All right, welcome to Function Stat Trig. Today we're going to find the inverse of a function. By way of warm-up here, indicate how you would undo each operation or composite of functions. So we're turning left. So we're at a particular place, or maybe we're going, but we're here. Then we turn left and we walk 30 yards. Then we turn around and walk 15 yards. So there we go. We have to just continue going, and we're back where we started. Multiplying a number by 1 2/3. How would we undo that? Now, one solution to undo that is just divide by 1 2/3. Good. So in this case, we can look at it from a different perspective by multiplying it by the reciprocal. So we can look at it by a division problem. We can look at it as a multiplication problem. Someone could have said, we could have multiplied by 6 over 10. And the answer is yes, you could have. Multiply by 6, divide by 10. You'd still get the answer. Now, notice I can reduce this fraction, but it still would work. All right, next, we are adding a number to 40. Whoa, look at my semantics there, holy. Then we're dividing the result by 1/2. So how do I undo that? We're taking the fifth power of a positive number, so we have a here. We're taking the fifth power, and then we're taking it, taking the positive square root. Taking the positive square root. So how are we going to undo that one there? All right, so if we were to algebraify it right here, we get the square root of a to the fifth, and we can square that whole thing and then take the fifth root. So I could have rewritten it like this and then said raise it to the power of 2/5, because when we multiply these exponents, they drop to 1, which brings me back to a. So we take a number and we add 40 to it, then we divide that by 1/2. So if I multiply by 1/2, that'll kill that, and then I have to subtract 40. So that's the process. Multiply by 1/2 and subtract 40. All right, so today is far less complicated than the domain stuff that we talked about in the previous days. So let's walk through situations of what's called inverse. Now, some things about inverse, something like I tie my shoe. So the question is, how do I get back? How do I get back to my shoe being the way it was before? So I could tie my shoe and then untie my shoe. That's one thing. Now, some things in life do not have inverses. For example, if I have a sandwich on the table and I eat that sandwich, it goes into my mouth. Boy, that is the ugliest person I've ever seen. All right. What's the inverse of eating that? True, but if I puke it, do I have a sandwich? No, I have Fruit Loops, right? So I can't actually put it back into sandwich form. So there is no inverse of that one. So let's see here. In most cases, algebraically, we can at least find an inverse. So if the volume of a cube can be found using this super secret formula where E means edge, so where E is the edge length, and you know that a cube was 250 cubic centimeters. In that case, of course, we place it here, and E to the third, and then we say, as was said before, we're going to take the third square root. We're going to take the cube root there of both sides, and so after we plug that into our handy-dandy calculators, we get approximately, not 2.3, 6.3? So approximately 6.3 centimeters. And of course, you can check it just by plugging the equivalent 6.3 and cube that to get your result. So notice here, I have a cube and I can undo that. If I add something, I can subtract it. If I multiply, I can divide. So we're going to talk about how we can undo other functions and not simply just a single operation, but something that has 5, 6, maybe 10 steps or whatever. Okay, so a function can be considered as a set of ordered pairs in which each first element is paired with exactly one element one element, excuse me, second element there. Exactly 1 second element. What do I mean by that? Is that your x's and y's? Your x's, if I have a 2, it's got to map to exactly one term over there, a 3. For example, the 2 cannot map to 2 different things here. So it's got to map to exactly one thing over on the other side. In other words, every time I put in a 2, it's consistent. It gives me out a specific thing over on that side. Okay, so if you switch the coordinates in the pairs, the resulting set of ordered pairs is called the inverse. So if we just have, we don't know what this function is right here. The function just says, when I input a -3, out comes this. When I input a -2, out comes this, etc., all the way down the line. So the inverse of that says, what function inputs this and outputs that? So it's probably easiest to put it in a table of values, but we could also say that the inverse, and we can just describe it in this way. -5 outputs a -3. And the 0 should output a -2, like so, etc. So I've done the reverse of each one. The y now becomes my independent variable, and I enter it to go backwards. Now notice here, every single time I input a -3, which is only once, I get a -5. Every time I input a -2, I get a 0, which is only once. Okay? So this one right here is a function. If you were to plot the points, it would pass the vertical line test. However, is this one a function down here? Is this inverse a function? Let's see. I input a -5. Do I input a -5 anywhere else? Oh, right here. Look. I input a -5 to get a -3, but again, I input a -5 to get a 3. So that's inconsistent. So this one is not a function. Now, there is no rule that says a function will always give you a not function for the inverse. It just happens in this case that it did not. So sometimes both will be a function. Sometimes it'll happen like this. All right, your turn. And if you prefer to write this as a table and then flip the table, you can do that. Take a few moments to do this one, please. So let's look at this one. I prefer the table because the table helps me to see whether or not it's a function. So this is the inverse, so hence I labeled it. The 1 maps to a 1, the 4 maps to a 2, the 9 maps to the 3, the 16 maps to the 4. Is this a function right here? Yes. Yes, it is, because look, there's no repeats, so automatically on the x, it's got to be a function there. How about the original? It's probably called a function, but is this a function up here? Yes. Yeah, because again, the x values there don't repeat. So this function, the inverse, yields a function also. All right, so what is, describe h and its inverse in words. So as you look at the pattern here, 2 to a 4, 3 to a 9, we see that that's the square function. And this one goes the opposite, or the inverse, and we call that the positive square root function. Yes. So here we are. If you are given information to find the inverse, all you need to do is switch the x and y. And that's it. You're done. You've now found the inverse. Now, your TI calculators can't actually calculate if you put y on the wrong side, like you switch those. Your TI won't calculate this, or won't be able to graph it. However, but Desmos does. If the inverse happens to be a function, it's actually best then to solve for y there. And learn to spell. Solve for y. Because now y would be embedded. So in this case, given the equation for the inverse of this function, this one's not overly complicated if you recall from how to graph this real quick. We quickly see this is a parabola because of the square. We see that it opens downward because of the a being negative. We also see this right here is going to be my vertex right there. If you remember or know that the pattern looks like this, you go down 1, right 1, and then down 3, right 1, and left 1, and then down 5, right 1, and left 1. So I'll give you... Now the question is, how do we now sketch the graph of the inverse. Now, by the way, the inverse is simply just replacing these, switch these. So this is what the inverse looks like. Using Desmos, we can simply plug these in, and it will graph it for you. Your TI will not, because of the nature of the fact that this is not a function. And we'll see momentarily. So how can I graph this if I don't know any super secret rules about graphing this? Well, the idea is simply this. If, according to this, when I put in a 0, out pops a 4. The inverse, we have to flip it. So instead of saying insert a 0, output a 4, we're now switching that to be a 4, 0. So that means I'm going to put the point over there. At 1, the original function gives me a 3. So I'm going to flip that, the 3 and a 1, right there. And I'm going to reflect it off the, reflect this across the x-axis there. So I'm just going to continue that journey here. This one here is a 2, 0, which means 0, 2 is going to be my next point, and that reflects there. And this one here is at 3, negative 5. So when I switch that, I get 5, or negative 5, 3, and down there as well. Oops. Okay. And now I'm going to rotate so I can graph this a little bit easier, or connect the dots, la la la, like so.
Oh, you can use those to make a heart.
Good. So what do we notice?
I see it.
So there's your heart.
Oh.
Right. Cute.
I was thinking more of like a...
Okay, I know. Math is the language of love, and there's a proof right there. I know. Hey, baby. Nice parabola. Okay. So let's notice some things here. What do you notice about the graph here? Well, notice if I just take the blue and rotate it, if you take the blue and just rotate it, essentially you get the graph. So what's something that we notice about the graphs? That the inverse is rotated 90 degrees. But there's something else you could observe, maybe. But if you were to graph this line right here, which is called the y equals x, so that's the parent function for linear, what do you notice? Well, it's this point here is reflected exactly across that line. So not only is the inverse rotated 90 degrees in this particular case, the inverse is reflected over the y equals x. So if you had this point right here, all you'd have to do is reflect it across there to make that other point. This point right here reflects across to there. This point here reflects across to there. So you could quickly draw that just by doing reflection or reversing the xy in order to find the individual points. So this point here maps to this point here, etc. Okay. And of course, the tables at the right, the x and the y are switched, as we see. And that's what we did earlier. We switch these, we get our function here, we know where our vertex is. So again, all we do is switch our vertex there to tell me the vertex of this other graph. Since the original function opens up, this one's going to open right. Since our stretch originally was a vertical by 2, this one's going to be a stretch horizontally by 2. So here we are. Here's my original function. And if I were to graph, of course, if you graph the x equals y, y equals x, which coincidentally is the same here, notice that these points just reflect across like so. So clearly this one here is not a function. Why? Because it doesn't pass the vertical line test. This one does pass vertical line test. This one does not. So function, not function there. All right, so when I have an x right here, the first thing that I have to do is this right there. So the first thing, according to the order of operations, is subtract 3. Next, we are going to take the reciprocal. Because if I have some number downstairs here, let's say after I subtract 3, I have 7. Well, now this says write it as 1/7. So this part right here says take the reciprocal. And lastly, I'm going to do that right there, add 4. Now we have to inverse. So inverse is not just about switching the points, but it's also about switching the direction of the activity that we just did. So how would you describe the inverse process here? Good. Now going backwards, we're going to subtract 4.
Oh, I see. You have to actually do it back.
Next, what are we going to do? Now we're going to take reciprocal. That's French for reciprocal. Holy monkey, learn to spell. Reciprocal. I just made that up, actually.
No,
False news, fake news, fake news. Watch out.
the same thing, though.
Lastly, we add 3. So how do I write that as a function? How do I write that as not a function necessarily, it might be a function, but how do we write that as a formula? I ran out of space there, so I'm going to do so over on the side. You have x. We just said I'm going to subtract 4. Then I'm going to take its reciprocal, and now finally I'm going to add 3. So here is my inverse right there. There's my inverse. B of x, it tells us to call it b. B of x is that. Now our job is to evaluate the composite of a with b of 8. In other words, first put 8 in this function, get a result. Then take that result and put it into this function. So go ahead and walk through that real quick. You're going to do b of 8 right here.
Babe, he's trying to catch us.
And then you're going to pass that answer on to a of x and finally get a result. So let's see the magic here of what the nature of inverses is. The nature of inverse is to get back where you started, right? So let's see here. Input an 8 into my inverse. Output is a 3.25. So if I put a 3.25 into my a, I get 1 over 1/4 plus 4. Now, of course, dividing by a fraction is the same as multiplying by its reciprocal. So 4 plus 4 is 8. I put in an 8 and get out an 8. And that is the nature of inverses.
So if you were to put an 8 into the...
So, as a reminder, this is how we can calculate without getting too crazy. If we just call this function y, all we have to do in order to get the inverse is just to switch those two and then solve for y. So now I'm going to put x on the outside and 1 over y minus 3 plus 4. And now notice, as we're going to solve for y, now we're going to solve for y, we're going to undo over here exactly like you described up above. So I have to subtract 4 from both sides, subtract 4 from both sides. So I get x minus 4 equals 1 over y minus 3. Now, the next thing it says is to take the reciprocal. If you want to know what that looks like algebraically, it just says put a -1 there, which means if I put a -1 as an exponent here, I now get 1 over x minus 4 here, and over there I get x minus 3. And the last thing I have to do is add 3 to both sides. And so now my ultimate function here is y equals 1 over x minus 4 all plus 3, like that. So the other one was sort of not 100% easy, but over here you could kind of like think it out, okay? But you never really have to do that because all you have to do is switch the two, x and the y, and then solve for that particular, solve for y now, especially if it's a function. All right, so as we graph this, notice our original function is right here, so that's the red one like so, the red one like so. Next, The blue one is my inverse. Now, of course, this is my x equals y, and I just want to point out that as we bounce points, so for example, this point right here reflects to that point across over there. And the same thing happens here. Here's my red there, and it's going to bounce over to that point right there. Kind of like a vertex of this shape. So this vertex goes through here. This one's going to go through here. And again, we can consider what the asymptotes are as well. Remember that this -3 tells me that the whole parent function shifts over 3 to the right. And this +4 means the whole thing shifts up 4. So if I were to clear that one out just for a second here, notice here's one asymptote right here, which is up 4, and this one is right, left 3. Now, of course, the asymptote for the other one is now just switched. Now this asymptote is up 3 and right 4. So the asymptotes have also switched places. So the examples 2 and 3 that we just talked about tells us something good about inverses. That not all inverses are functions. So if you start with a function and you inverse it, you may or may not get a function, depending on the context. When the inverse of a function is a function, then it is denoted by this symbol right here, because when we give f a name, then that generally means that it's a function. So we read this as the inverse of f, or f inverse, okay? And the key thing about this one is to beware. This does not mean reciprocal. It does not mean reciprocal. So it does not mean 1 over f. So it doesn't say, don't take the whole function and just flip it upside down, okay? That is true in this case. If a is simply a number, then this means 1 over a. So for example, this means 1 over 2. 2 to the -1. It does mean inverse, but in the sense we're talking about inverse as in invert it, turn it upside down in this context. In this context, it doesn't mean turn upside down, but rather it means to undo, go backwards in a sense. All right. So finding the inverse of a function requires you to switch the x and the y coordinates. Therefore, switching the domain and range of the original function will give you the domain and range, misspelling, of, the domain and range of the inverse. So that's nice. All we have to do is flip those, and we know the new domain and range. And here's the key thing about finding, and just not just finding, but but proving that the two inverses, that the function and the inverse are indeed functions and inverses. Given any two functions, f and g are inverse functions if and only if. If and only if means it goes both ways. That f, the composite of f with g of x, is x. For all x in the domain of g, and the composite of g with f of x is x. So when you embed g inside of f, you get x. Or if you embed f inside of g, you end up, it simplifies to get x. So the best way, of course, is to walk through an example so that you see that. So example 4, using the inverses of the functions theorem to determine whether f and g defined by this are inverses. So there are two ways to do it. However, one way is just to take one of the functions, there should be an equal, this function right here, and just place it inside there and inside there. So that would be f with g of x. So we embed one in the other. Now, it actually doesn't matter which one you embed in which one. The important part is that you just take one of the functions and embed it over there. So let's walk through and see what we get. So this is going to be a complex fraction, so I'm going to give myself some space. So I'm going to say 2 times x minus 1 over 2x plus 4 all minus 4. And then down below is x minus 1 over 2x plus 4, all plus 1. All right, so let's see here. If I were to take the 2, remember, distributing the 2 here does not mean distributing it to everywhere. Remember that this is 2 over 1. So the 2 is going to distribute only to the numerator, not to here. So let's do that. So now I get 2x minus 2 over 2x plus 4 minus 4. In fact, instead of doing the minus 4, I'm going to go ahead and find a common denominator. And if I write the 4 with the common denominator, 2x plus 4, so 2x plus 4 is there, 2x plus 4 is there, which means I have to quadruple the 2x plus 4 there. Now all that is over, and I'm going to go ahead and find the common denominator here, plus 2x plus 4, 2x plus 4. So the denominator is a little bit easier to clean up. I'm going to combine these ones. X plus x is 3x. X plus 2x is 3x plus 3, all over 2x plus 4. So that's what the denominator looks like there. The numerator, I'm going to do 2 steps at once. I'm going to distribute this and distribute the negative 4 and combine like terms. So negative 4 times 2x is negative 8x, plus that gives you negative 6x. And negative 4 times positive 4 is negative 16, minus 2, so that's negative 18, all over 2x plus 4. Now, here's what's nice. What does division mean? Multiply by the reciprocal. So I'm going to write this here, but all I have to do is flip this guy right there. So negative 6, I'm going to go ahead and distribute or pull out what I can, if there is anything. So I just factored right there. And here I'm going to factor as well. Now I multiply.
It's not 4.
Thanks, 2, right? And then down below, now the 3 comes out, and I get x plus 1 there. Okay. Now, ultimately, everything should cancel out if this is a function. Everything except an x should cancel out. Well, clearly here, these drop out because those are exactly the same. The 3 here reduces here, and that becomes there. But the x plus 1 and the x plus 3 do not reduce. And so in the end, we end up with this. Negative 2, x plus 3, over x plus 1. This does not equal x, so they are not inverses. So if we were to graph these two functions, so if we look here, the red one is right there. And if I were to reflect, trying to reflect it off this y equals x, clearly this here does not map to the blue right there. Because look, it's got to be equidistant. So it's got to map out to here somewhere. So with all that arithmetic that we did, the answer was no. But had we just simply looked at the graph, we would have seen that this one did not map to the blue right there. It almost seems like the red maps to itself when we reflect it, but that's not what we're looking at. We're looking at from red to blue, and so we see that it doesn't work out. So that's the easiest way to actually do it there. All right, take a minute and do this one. Go.